Hello and welcome back. Let's do one more example of comparing two populations' proportions. So in a medical study, 11,037 people were given aspirin and 11,034 people were given placebos. And what they're doing is they're seeing how many people would have heart attacks just going about their daily lives. Only 139 people had heart attacks when they were given aspirin. But 239 people had heart attacks when they were given placebos. So it feels like, since the numbers are similar, that more people had heart attacks when they weren't given aspirin. So we want to test the claim that aspirin reduces heart attacks with a 0.01 significance level. So our claim is just exactly that, is that aspirin reduces the risk of heart attack. And if we want to make this a little bit more symbolic, if we call P1 the proportion of people that have heart attacks when they are on aspirin, versus P2 the proportion of people that have heart attacks when not on aspirin, we're saying that P1, if aspirin reduces the risk of heart attacks, that P1 should be less than P2. The proportion of people that have heart attacks on aspirin should be less than the proportion of people that have heart attacks when not on aspirin. Again, the null and alternative hypotheses. The null hypothesis is always with equality, so it's going to be P1 is equal to P2. And the alternative hypothesis is going to be that P1 is going to be less than P2. Typically, we want our symbolic claim to be our alternative hypothesis. So in this case, we're just going to be testing whether or not P1 is less than P2. And our significance level is 0.01. Which is a pretty small significance level, but that's important for reducing error. Let's say in a medical question, we do want a fairly small significance level. So now we have to calculate our test statistic and our p-value, and what I want to do is I want to run through StatCrunch again. We did this for the last example, but it went by fairly quickly. So let's come back to StatCrunch. In statistic, we can come down to proportion stats because we're testing proportions, and we have two samples of which we know the summary of the samples. We don't actually have the actual data, but we have summaries of our two samples. So there were 139 people that had heart attacks while on aspirin, but it was 11,037 people who were being given aspirin, and I should check so I'm not just guessing. Yep, 11,037 people, but there were 11,034 people given placebos, but 239 of them had heart attacks. And again, so our hypothesis test for the difference in the proportions, again, we would our null hypothesis is that the difference is going to be 0. But if we come back to the alternative hypothesis, what I do want to write down really quickly is if I subtract P2 from both sides, what we're testing is whether or not P1 minus P2 is a negative number. So we want P1 minus P2 is less than 0. And this is all of our information. We know our successes in both trials. We know our how many people we tested, our hypothesis test, and we can compute that. And here's everything. So our z-stat is going to be negative 5.1907. So let's round that to four places. So z is going to be equal to negative 5.1907. Good, I remembered. And our p-value is in fact less than 0.0001. It's so small that all it's telling us is that it's too small to round to four digits. It's going to be less than 0.0001. So that's pretty small. But our significance level, So our p-value is a lot smaller than our significance level, so we can reject the null hypothesis. So we're going to reject P1 is equal to P2, which means that we get to safely conclude that P1 is in fact less than P2. So our conclusion is that there is sufficient evidence to support the claim that aspirin reduces heart attacks. Oops, can't write today. Aspirin reduces heart attacks. So, yes, since the people on placebos had nearly twice as many heart attacks as those on aspirin, it would make sense that we can conclude that that aspirin does reduce the risk of heart attacks. But we also saw another way to test the difference in proportions. We can use confidence intervals. So with a confidence interval, we have to have a confidence level, and we have to know whether or not our confidence level is going to be one-tailed or two-tailed. So what we're testing is if P1 is less than P2. And if we're just testing whether or not P1 is less than P2, that is only one tail. So our alpha here just corresponds to this one tail. So our alpha is 0.01. However, with a confidence interval, we want to have both a lower bound and an upper bound. So since this is a one-tail test and alpha is corresponding to just that tail, we have to also put an extra alpha on this top side. So that's also going to be 0.01. So that what's in the middle is going to be 1 minus the alpha on the left and the alpha on the right. So 1 minus 2 times alpha is going to be a 98% confidence level. So our confidence interval, again, we can come right back to StatCrunch. We can go stat, we can come down to proportion statistics. We have 2 samples, and we have a summary of the data. Again, we had 139 versus 239 people that had heart attacks. On aspirin, there were 11,037, and on placebos, there were 11,034. And now we don't want to perform a hypothesis test, we want to form a confidence interval, and our confidence level is going to be a 98% confidence interval. And one nice thing is we can ask it to make a confidence interval plot. You don't have to do this, this is not important, but it's kind of nice to see, and then we can compute. So let's look at all of these numbers here. So what we see is that we have the difference in the population, all of the numbers that we entered in, and we have our lower limit and upper limit. So let's round these to 4 decimal places. So this is negative 0.0131. So negative 0.0131, and that's going to be smaller than P1 minus P2. And our upper limit is going to be negative 0.0050. So the difference in our 2 proportions is going to be somewhere between these 2 numbers. But what you'll notice is that 0 is not between those 2 numbers. So this guy, we're confident, can't be 0, right? We're pretty confident that that P1 minus P2 isn't 0 because it has to be between 2 negative numbers. Well, 0 isn't between two negative numbers, so we can reject the null hypothesis. And in fact, since P1 minus P2 is a negative number, we're confident that it's between two negative numbers, so it has to be negative. We're also confident that P1 should be less than P2. So we draw the same conclusion. So we're confident that aspirin, the proportion of people on aspirin who have heart attacks, is smaller than the proportion of people not on aspirin that have heart attacks. So this is just a very quick example to show you how quick these can be done using StatCrunch. The very last thing that I'll mention is if you are about to conduct an experiment, you can actually work out in advance how many people you would have to test, how many samples you would have to collect in order to be confident at a certain range. So if we want to have a particular confidence level, let's say we want to be 95% confident, 99% confident, and we know how big of a confidence interval we want. You know, it's one thing to have a huge confidence interval to say, oh, the value is somewhere in there, versus, oh, we've got a little itty bitty tiny confidence interval, and we want our value to be in a really small range. We want to be more precise. Well, we know exactly how big of a confidence interval we need. You have to calculate the z-score, but all it is just a simple formula. And this is the formula for proportions. So let me do a quick example. It's nothing more than just plugging some numbers into a calculator, really. If you want to compare men's and women's smartphone use with a 95% confidence level and an error smaller than 0.03, so we want our confidence interval to be pretty small, how big of a sample is needed? Well, we know that our sample size, our two samples, are going to have to be n, which is going to be our z-score squared over 2 times e squared. Well, we know 2 is just a number. E, our error, is given to us. The only thing that we have to find is our z-score, which, if we're at a 95% confidence level, that means that we want 95% confidence in the middle, which means that I want 2.5% confidence on either end. So if we come back to StatCrunch, we can open up our normal calculator, normal distribution calculator, and we want, so 2.5% is 0.025. But that should be the area. I entered it in the wrong spot. So the area should be 0.025, and that's negative 1.96 if we round to two decimal places. So negative 1.96, and we are squaring that. You plug all that into a calculator, and you get 2,134.2, rounding to the tenths place. But it's kind of hard to ask. So if we're comparing men's and women's smartphone use, we're asking people about their smartphone use, and it's hard to ask 0.2 people about their smartphone use. So we'll err on the side of caution and ask, don't want to say that that's equal, and we'll ask 2,135 people, as in 2,135 men and 2,135 women. We don't want to go under this this number because that won't be enough. We will round up and ensure that we have asked enough people, and that's where I'll stop.